In this video, part A of vectors work done by a force, we're going to have a look at the work that is produced or the result of a force acting on an object. And we're going to have a look at its horizontal motion or movement. So we're going to particularly look at the scalar projection of the force multiplied by s, and s represents the distance of s meters. So let's see this in action. In situation 1, we have a force of 200 newtons and it's applied at an angle of 30 degrees inclination from the ground to move an object, which is represented by the black rectangular box. We want to move at a distance of 5 meters. So what we want to do is calculate the work done by this force for it to move 5 meters. Okay. So what we want to do is have a look at what result that force is producing. So obviously by this really nice example, we're dealing with right angled triangles here. And the resultant we're going to have, we could call it capital R, is going to be in that positive movement horizontally. So if we look from this angle, we can see that we want to know the adjacent side, and we know the magnitude of our force, which is the hypotenuse in this right angled triangle. So we could say the cos of 30 degrees should be equivalent to the result, or the magnitude of that movement, divided by a force of 200 newtons. So the resulting magnitude, or scalar, is 200 times the cos of 30 degrees. So we've got 200 times the cos of 30, which is root 3 on 2. And that's going to give us a magnitude of 100 times root 3 newtons. So that just tells us the resulting force that's going to happen. But what we want to do is move the object horizontally 5 meters. So we want to produce the work done by this force is going to be the force result itself times by that distance that we want. So we've worked out the resulting force, or the projection of the force, as a scalar. So let's just write that. This is the scalar, the size of the projected scalar projection of the force. So that's just what value that force has created as the result. And we want to do that for 5 meters. So that's going to be 100 root 3 times 5. And that's going to produce the work as 500 root 3 joules. That's our final work done. In our second example, we've got something a little bit different here. We've still got a force represented by F that is inclined by 30 degrees, as in our previous example. But what we've got is our object has a weight of 150 newtons, and it's being pulled along by this force. We can see that we've got a direction of motion of which way we're going to go. The motion of the object, however, is opposed by a horizontal force of 10 newtons. So opposed means the opposite direction. So we've actually got an extra 2 things happening here. We've got the weight of the object pulling it, counteracting some of that weight, and the opposing force. What we don't have in this example is what is the size or the magnitude of that pulling force. But from our diagram, what we can see is for that force to have its result inclined 30 degrees, it's counteracting the weight of that 150 newtons. So it's certainly doing pulling up the opposite of that. And what we end up seeing here is a right-angled triangle. We're counteracting that 150 newtons, and we have the force going in that direction with an angle of 30. So once again, we have a right-angled triangle. We can now find the magnitude of that force. So in this case, we're going to use sine, because if sine of 30 degrees is the opposite over the hypotenuse, the magnitude of that force. So the magnitude of the force is going to be 150 divided by the sine of 30, which is going to give us 150 divided by a half, which is 300 newtons. What we next want to find is the magnitude of the resulting force in the direction of the motion. So we can see that we've got our direction of motion here. So given that we've got the force that's pulling us at an inclination of 30 degrees, but we also have to remember that we've got this opposing force here. So what we're going to do first of all is go back to our right-angled triangle that we had in our previous part, where we've worked out the magnitude of the force is 300, and we had an angle of 30 degrees. We need to find out this value here, which is our scalar projection of the force onto that direction that we're going to be travelling in, onto that object. So looking from the angle here, we can see that we want to find this projection using cosine, because the cos of 30 degrees is going to be the projection over the force. So the projection is actually worth 300 lots of cos of 30 degrees. That helps us because that's what the force is projecting on that object. It's pulling it in this direction. So the result of the force pulling it in that direction is 300 cos of 30 degrees. However, we're going to have to take away that 10 newtons, that's the opposing force. So this results in 300 times the cos of 30 subtract 10. Now we know the cos of 30 is 3 root 2. So we've got 300 times 3 root 2, root 3 on 2. And we're going to subtract 10 from that. So we end up with the result as 150 root 3 subtract 10 newtons. So what this tells us is that the size or the magnitude of that resulting force in the direction of the motion. So now what we want to do is actually work out the work done. What work in joules is done by this force? Well, that's just the result that is produced from the force, taking away that opposing motion or a horizontal force, and we want to move it 15 metres. So multiplying this, we end up with 150 times 15 root 3 subtract 1 joules. So I've multiplied 15 and just taken out a common factor of 150. And this equates to 3,747.1 joules. So let's just go back and recap this situation. What we've got is an object. We have got a force acting upon it, inclined by 30 degrees, and it's also counteracting its weight, and that's producing this resulting force. The projection that the force is placing on this body, subtract the opposing force, and we've called that our result, capital R. Now that's the direction that we've got in newtons, but the actual work done by this in joules is using that motion direction and the fact that we want to travel 15 metres worth of that. And we end up with our solution of 3,747.1 joules.